Good morning and welcome back. This is your teacher, Chunxu Zhang, as second semester of electrodynamics. Due to the outbreak of COVID-19, we will change our learning mode to distant learning. I will record the file, the material and upload to YouTube so you can learn by yourself. So today we will continue our study about special relativity, chapter 11. So first, let you know today's course is electrodynamic 21.518. Okay, so I will continue our study about section 3, covariance of electrodynamics. That means the electrodynamic equation will invariant in form. Okay, in a special theory of relativity, Newton's law has been radically changed, radically modified. For example, Newton's law tells us that F equals ma. However, we know it's incorrect in special relativity. So how about F equals, that's not good, gamma ma, that's still incorrect. O gamma m dv dt plus t, still not good enough. So I will show you becomes dp dt. That's the ordinary force. However, how about another force? Another force called dp over d tau. P is the momentum, O the energy. Remember, okay? So it changed a lot. Newton's law has been radically changed. So I will show you electrodynamics do not change that much. Its electrodynamics will be correct. Will be electrodynamics law do not need any modification. Also, that's good. But how to prove they satisfy? They are the same in form, are invariant in form, satisfied from different inertial frame to another inertial, from this inertial frame to another inertial frame. They are still the same. How to prove? To prove that, we should change the form from their normal representation to a better form. Our purpose in this section is to prove that EM waves are covariance. They covariant in form. They invariant in form. How to do that? We will casting them into relation between 4 tensors of the set of the same rank. For example, C, T, X, Y, Z. That's the 4 tensor of the first rank. How about others? For example, E over C and momentum. That's also 4 tensor of the first rank. How about others? Okay, we will first define four tensor in terms of known EM quantities, such as rho A, actually zero, such as oh, sorry, there's a typo. Rho and J and phi and A. Okay. Another four tensor to be determined. And of course, we will determine the force, Lorentz force. So today I will cover only 8 pages from page 39 to 46, not too much. Today we will cover just a few pages only. Okay. And the first tensor of the second rank. Of course, we will consider the four Maxwell equations. And we will prove that the laws are invariant or covariant and justify the defined quantity to be legitimate for tensors. Furthermore, Lorentz transformations of these tensors will yield the transformation equation for various EM quantities. Jackson switched to the Gaussian unit from starting from chapter 11. So I'm sorry, we will change from SI unit to Gaussian unit from now on. Okay, I will still write the Gaussian equation for your reference. Okay, that's the first one. Second, so first, let's define the most important quantities. For example, current, potential, wave number, and the four vector of the same form. We have defined the four potential here. Four potential, four momentum. What else? Here is another one. Four current as J new, C rho, JX, JY, JZ here. Okay, and also C rho, that's four current, the same dimension. Charge density times the velocity is the current, and we will use its form and use it to form a relation. What's this? Divergence J equals partial mu J mu equals partial mu J mu, up, down, up, up, down, the same. We can prove this using the metric tensor or the norm tensor. G alpha beta or G alpha beta. Then equation 36 gives the law of conservation of charge. This one gives the conservation of charge. That is, oh, so that's the equation we're familiar with. We already, this one will be invariance. So the conservation of charge will be covariance, that is invariant in form in all the Lorentz frame. Okay, so let me write down again. Divergence J partial rho, partial t equals 0. So this is SI unit. And this one also Gaussian unit, but still the same. That's the definition of J as a 4-vector leads to the covariant representation of EM nodes. This in turn justifies the definition of J as a 4-vector. So this is a definition, but later we justify because of this one. It's just like A dot B or divergence J equals 0. So it's a conservation of charge. So it satisfies the Lorentz transformation. So for example, they have a common axis move in. We have a two frame K and K prime. K prime has the relative motion V0 relative to K. And so they have a simple relations because J and rho forms a 4-vector. Prime system and unprime system, they are transformed through the Lorentz transformation. Okay, so that's the first, this page. What else? What else? Okay, second, for potential, we have phi AX, AY, AZ. AX, AY, AZ here. For Griffiths, SI unit, this is Gaussian unit. And we can write the covariance relations. For example, now we have 4 current, and we can rewrite the wave equation into this form. Laplacian, 1 up, 1 down, 1 down, 1 up, the same. Okay, Laplacian A. A is a potential, so it looks like this one. So we have 2 equations. This one, this one. The right-hand side is the wave equation and source. Wave equation and source. Okay. How about this one? This one will give us this equation. It should be invariant. Covariance, that is invariance in form. Just a moment. Jump too much. Okay. And in terms of SI unit, it's shown here. SI unit shown here. Okay. That's the SI unit. And what's this? Lorentz gauge. That's the Lorentz gauge. And Lorentz gauge will be independent of the reference frame. So looks like Lorentz gauge automatically satisfy the Lorentz transformation. Okay, that's Lorentz gauge. And this is the wave equation. And wave equation together with inhomogeneous wave equation is satisfy Lorentz gauge. Satisfy these relations. This again shows the consistency of A being a 4-vector. So here we just define a 4-vector as this form. And then we prove A is a 4-vector because it satisfies these simple relations, such as Lorentz gauge wave equations. Okay. This again shows the consistency of A being a 4-vector and being a covariant law, invariant in form. The Lorentz transformation between the Lorentz transformation between A and A prime is here. A and phi vector potential and a scalar potential, just like the previous case is shown here. Is shown here. Okay, so we know in the previous case, Cj for current, and now we have four potential. For current, four potential. Phi A X A Y A Z. For current, zero current. Okay, we just derived two important equations of more than two: conservation of charge and Lorentz gauge equation, inhomogeneous wave equation. So A will satisfy the Lorentz transformation. What else? Let me give you more information. The source-free wave equation can be directly put into the covariance form, like this one, easily. This one is a four wavenumber. Four wavenumber. In this case, K is W over C, four wavenumber. So what happened here? Then K, that's four position. K prime dot X prime, just like A prime dot B prime equals A dot B. Four vector. So the same conditions. That's the invariance of the phase. The phase from different inertial frame should be the same. By the same argument, we know this is four position here. So four wavenumber will be a four because they satisfy these relations. By the same argument, we find that K defined in 43 is a legitimate four vector. 合法的 legitimate four vector. Its Lorentz transformation gives this one. This is famous relativistic Doppler shift. One more time. So just like we have two rest frame, relative motion. So K and omega can be transformed through these simple relations. I will give you an example next time, not this time. So we have three, four current, zero J, four momentum, four potential, phi A, four wave number, C omega K. Okay, that's the fundamental law. So we already have this one. Now I will give you more information. The field strength tensor of the second rank. The problem is we have all the quantity. We just define all the quantity except the E field and B field. E field, we have ES, EY, EZ. E field, we have three components. E, X, E, Y, and EZ. Yeah, we have three components. And what happened? sorry. We have three components. Just erase this one. We have E, X, E, Y, E, Z. On the other hand, magnetic field, we have BX, BY, BZ. So obviously, they're unable to form a four-vector, four tensor of the second rank. How about four tensor? They're unable to form a four tensor of the first rank. That is four vector. So let's try four tensor of the second rank. But four tensor of the second rank is 4 by 4, 16 quantities, 16 components. How to form a four tensor of the second rank? Here is a possibility. We have 6 components. So for a symmetric tensor, we have symmetric 4 diagonal and off diagonal. Totally, we will have 10 components. But axisymmetric field tensor, we have just 4 components. So just like this one, it's a 4 components. So by changing the index, they will differ by a minus sign. So this is anti-symmetric. So definition of this one is here. Okay. So definition of this one, how to define this one? Actually, we will discuss this issue when we have time. But remember, for anti-symmetric 反对称的, we have just 6 components. 1, 2, 3, 4, 6, 5, 4, 5, 6. You might wondering, how about dx, dy, dz, and hx, hy, hz? We have 12 components. But for vacuum, because here we discuss relative motion, so we prefer free space. Therefore, we won't discuss this one. These are closely related to 6 components shown here. Closely related to 6 components only. Okay. So anti-symmetric field tensor, just defined here. And we know it's related to scalar potential and vector potential. Later on, we will show you it's related to this one. Or you can prove by yourself easily, like this one. Like this one. B field equals curl of A. Yeah, you can prove easily using this one. So maybe it's a homework or a problem in our final exam. Okay. So it's an anti-symmetric second rank tensor. What's the difference between up and down? If you want to lower the index, this is upper index. Lower the index, just use the norm tensor or metric tensor. Sum over delta, sum over gamma. Then we will obtain this one. What's the difference? Just differ by a minus sign. Positive becomes negative, and negative becomes still negative. Okay, this part is still the same, and this part from positive to negative. This part is still the same. So the element of F alpha beta are obtained from F alpha beta by putting here E equals minus E. You can prove by yourself easily. Actually, no difficulty at all. You can prove by yourself. Okay, so keep this in mind. You may have a chance to prove this property soon. Okay, next page. Okay, so we will examine the inhomogeneous equations. What is the inhomogeneous equation? For example, this one, inhomogeneous Gauss law. Gauss law. And Ampere's law with Maxwell correction. Okay, it's SI unit. It's Gaussian unit. Gaussian unit. G-A-U-S-S-I-A-N. So the difference is 4 pi here, nothing. 1 over C here, nothing. Okay. Personally, I prefer SI unit. I prefer this unit because this unit is much easier to remember. No other coefficient. But here we have extra coefficient. Extra coefficient. And will be easily confused. Okay. So a divergence of a 4 tensor of second rank will be a 4 vector. So this equation are invariant. We just write it down without proof. We just write it down because for current, we have 4 components, rho, C rho, J. That's the 4 current at the right-hand side. And left-hand side, we have a divergence F. It's a 4, and that's a 4 by 4. So this one operate on, so it's not easier to understand from these viewpoints. Therefore, in terms of not easy to understand, first column, first line, okay? Use a metric representation is not convenient. It's inconvenient in this case. We have to change. So if possible, let's use index, not metric representation. If you want to study how to change from the index to the metric representation, you can check Griffith's lecture notes. I have proof in Griffith's. 2 equations are covariant, okay? Invariant in form because this one, they all satisfy these relations. It's a 4 current and it's a 4 tensor of the first rank. So it's just this equation. And this one satisfy. Just form a 4 vector, 4 tensor, 4 tensor of the first rank. Let's just form a 4 tensor of the first rank. The inhomogeneous equation. What is the inhomogeneous equation? Divergence B and curl of E plus 1 over C partial B partial T equals 0. That's homogeneous equation. Homogeneous without source free. And here we will use 4 tensor of the third rank. 4 tensor of the third rank. In this case, if lambda mu equals 1, 2, 3, just permute with each other. 1, 2, 3, 2, 3, 1, 2, 3, 1, 3, 1, 2. Permute. Then this one will be here, 0. And if equals to this one, another set, 0, 1, 2, 0, 1, 3, 0, 2, 3, then permute. Any other combinations? No, just 4. 4 set, just 4 set. How about 1, 1, 2? Remember, 1, 1 will give us nothing. And 1, 1, 2, you can study by yourself and see what's the difference. Okay, so 0, 1, 2, 0, 1, 3, 0, 2, 3. No more. We got this one. Otherwise, you will receive. You can prove easily. How about 1, 1, 2, 1, 1, 3, 2, 1, 2, 2, 1, 3, and see what will happen. Write it down by yourself, and you will have better understanding. Okay? So we still have 2 pages. Actually, yeah, we still have 2 pages. Any questions so far? You can have a 2 minutes break. Think about it. I use notebook together with iPad. It's very convenient to write, use an Apple Pencil. However, it's a little bit inconvenient because the connection between Apple Pencil and a notebook is not that good. So we have this one inhomogeneous equation. And we also have this one. Looks different from our previous understanding. Oh yes, the same. The same. Here, lower index, upper index. This gives the set of Maxwell equations in free space, in vacuum, nothing. This shows that Maxwell equations are covariant, as well as justify the definition of F as a tensor of the second rank. So if we want to E field and B field transfer from one coordinates, one inertial frame to another inertial frame, we can use Lorentz transformation matrix two times. Give the transformation equation for E and B. Okay, that's very convenient. In the matrix representation, this can be written as this form. A is the Lorentz transformation matrix. O you can write into this form. Into this form. The parallel component do not change. Parallel component of E field and B field do not change. But the perpendicular component, in this case, the parallel component is Z direction, for example, is Z direction. So the Z parallel E field, parallel B field in z direction will be exactly the same. The same. However, the perpendicular component will be this one. Okay. I just write it down without proof. I just assume you have studied Griffiths before, because Griffiths has derived this equation using Lorentz transformation, using length contraction easily, using a solenoid, using a parallel plate. Okay. Using the ideal conservation of charge. So Griffiths, if you do not understand how to derive this equation through the Lorentz transformation, yes, we can prove that. However, if you want to fully understand how to derive this equation, I strongly recommend you to study the course material of the Griffiths. In equation 46, V0 is the velocity of frame K relative to frame K prime relative to frame K. The parallel and perpendicular refers to the direction of V0. In this case, Z, okay? Okay. You have two strategies. We just show you the field tensor, F, the field tensor, FIELD tensor. The field tensor, it consists of E and B, okay? And if you agree with this one, previous page, then they will transform, follow this rule. That's strategy. But if you don't feel comfortable, you can study Griffiths course material by yourself. Okay. Last page. Covariance equations. That's the fourth. Next time I will talk about this issue again. But today I just show you, go back to this page. Go back to this page. Remember, we said Newton's law has been radically modified. And now I will show you what is the Lorentz force looks like. That's the Newton's law. We define a covariance equation. Newton's law. No, it's a 4-vector. And momentum comes from, the tau comes from here. How to derive this equation? We can derive this equation through time dilations for momentum. Okay? And the tau is the Lorentz scalar. Appendix A time dilations. That's the regular equations. So it's different here. E F alpha beta momentum. So what's the relation here? Remember, P is actually a momentum. So P beta is C E P minus I. Okay. Minus P. And check. And here, the tau over dt, F alpha beta here, that will be related to here, gamma mv. So if we define a gamma here, in this case, 1 over gamma mc. So it will help us to derive Lorentz force and the change of the energy or the work done by the E field. Alpha equals 0 related to the work done by the E field. The work done by the E field is shown here, the rate of change of the energy. The rate of the change of the energy. The rate of the change of the energy. Okay? That's the first one. And this is the force we know. That's the Lorentz force. So we have two forces. One is, the other is dp over dt. That's the force we know. Normal force. But this force is Minkowski force. Okay, Minkowski force. Relativistic equation of motion. Alpha 1, 2, 3 is the relativistic equation of motion. Relativistic equation of motion. Lorentz force QE plus 1 over C V cross B. We know the speed of light is the same in all inertial frame. That's the universal speed of light. So it's a invariant. In this case, E will be another invariant quantity, Lorentz invariant. The charge E must be a Lorentz invariant. Otherwise, different observer will see a different E. Okay, that makes sense. Just imagine we have a charge here, and it has a 1, 2, 3, 4, 10 flux. The flux is associated with the charged particle, positive. And when this particle moves, they still have 10 flux. And this particle moves very fast. The flux should be the same, should not change. It's a scalar, it's a quantity. It's a quantity that do not change with inertial frames. So the charge will be invariant quantities. Okay. Okay. So although we just give you we just from page 39 to page 46, just 8 pages, not too much, but we provide many information for you. So you should study by yourself carefully. Study by yourself. We assume that you already study Griffiths. Some previous course already tell you how to derive this equation. Here is a summarize. I will provide some link for you so you can download the file and study by yourself if you do not study Griffiths before. If you do not study the special relativity in Griffiths before, then you will have a chance to study by yourself. Special relativity has been used in many fields. So it's a cornerstone for modern physics. I strongly recommend you to study special relativity carefully and consider our lecture notes as a reference. Okay, so I will stop here. I will stop here and see you next time.